Okay, thank you for coming in, getting the sheets from the front. You don't need that right now, though. Okay, so you're answering the question, what's in the bubble? So choose the best answer, and then I want you to explain in complete sentences what you think is in the bubble.
No, the bubble is
Read the thing. You have about 2 minutes. About 30 seconds. Okay, let's look at this together. Hannah is boiling water and a glass tea kettle. She notices bubbles forming on the bottom of the kettle that rises to the top and wonders what is at the bottom. She asks your family what they think, and this is what they say. Okay, so you have Dad who thinks it's heat. You've got Calvin who thinks it's filled with air. You have Grandma who thinks it's an invisible form of water. And you have, let's see, Mom, who says that nothing, they're empty. And then Lucy says that the bubbles are basically contain oxygen and hydrogen that are separated from the water. Okay? And before we go into what's right, what's wrong, I'm going to take a moment and I'm going to try to remind you of a few things. Okay, and basically reteach some things. What I would like you to do is, at this point, is wherever you stopped writing, I want you to draw a line underneath that. This is going to be our line of learning, where we have, this is what we originally thought, and it may be right. Or we may want to adjust and change that, revise it as we go. Okay? So, and here's a incentive. Whether you get it right now or whether you revise it to get it right, either way, I've got a treat. Got some leftovers from one of our labs, so I think we might as well get rid of them. Okay, so anyway, let's see. I don't even want to take a poll of who answered what. Let's just get it right. Okay, we're talking about water, and water has a chemical compound of what?
H2O.
H2O. All right. And now I found this animation here that I'm going to use. This animation shows individual atoms. They're stacked together and they're moving. What state of matter would this be in?
Solid.
Solid. Okay, so we all, even though it's moving, right?
Yeah.
Okay, it's moving, it's vibrating, so it's going to be a solid. Okay, so, and as I heat it up, what's going to happen?
They're just going to get a bit more excited. So like gas.
Yes.
Big gas.
It's an exciting time for them. They're getting excited here. They're going to start to move past each other and flow past each other. Oh, what's that?
Oh, yeah.
Yeah, that would be a gas coming off of the liquid. So there's a little bit, this is a transition state. Okay, so we're going from liquid to gas. And if I kept on heating up, what's happening to those atoms?
They're evaporating. They're speeding. Well, not evaporating. They're speeding out.
They're speeding up, bouncing off each other, they're spreading out, they're expanding. And remember when we have said before, like expand and then contract. What I want you to understand is, when it went from solid to liquid to gas, what happened to the size of the individual atom? Really? Nothing. It stayed the same. Exactly. So when we talk about expansion, we're not talking about the individual atom getting bigger. Let me show you the difference between a neon atom and an argon atom. Argon's bigger. Argon has how many shells? Can someone tell me how many shells argon has? Raise your hand. Lily says 3. Is that correct?
Yes.
Deontay, what tells you what is how many shells? It's in period 3. Fantastic. How many shells does neon have? 2. 2. Okay, so we see that the shells do have something to do with its size and its mass as well. Okay, so we see this, right? This is nothing. Is this anything new to anyone? Fantastic. Okay. So, all right. Now let's look at oxygen. Let's go back to solid state. This is solid oxygen. You have to be pretty cool.
How does oxygen, what is it all?
It can be with pressure and with temperature. Using those combination there, it can be. But let's see. As we heat it up, why are they in pairs?
Because they don't like to be O2.
They do not like to be alone. Okay. Let's see. Somebody raise their hand. Why are they in pairs? Okay, Jacob?
Because the oxygen particles are bonded.
That's exactly right. The oxygen molecules or oxygen atoms are bonded.
There's just like one
Excellent.
chilling up there.
Yeah. So they are bonded together. So these oxygen atoms are bonded together. Do we understand that? They are bonded together. So they go in pairs everywhere they go. Do you see that? Do you see them separating from each other?
Yes.
No. Pairs, right?
I don't have the individual particles.
Good. What would it take for me to separate this bond, Braxton? Hold on, Braxton. What would it take for me to separate this bond? A chemical reaction. Do we understand that? That in order to break a bond, in order to break a chemical bond, you're going to need a chemical reaction. All right? So let's go here. Let's look at water.
Solid.
As a solid. Connected together, right? Now, water, H2O, has this phenomenal characteristic in that it is actually bigger, has more volume as a solid than it does as a liquid. Remember, like if you put water in a container and put it in the freezer And it freezes. What happens to the container? It expands. It gets bigger.
It's like when you get a Coke and
Exactly. And that's not normal. That's not the normal thing that we see. Exactly, contraction, right? But notice how the molecules are it's almost at an angle and everything. So if I were to look at this, and as I heat it up, what do you think is going to happen to the H2O? Are they going to separate from each other?
Yeah. Well, no, I thought it would be individual particles.
Good. So this is a compound. It's also a molecule, right? And the molecule is not going to separate itself. It may separate from other molecules,
Yes, that's fine.
but it's not going to separate from itself. So we're not going to have lone hydrogen and oxygen flying off. But look what happens as you heat it up. Watch what happens to the volume. Watch the volume.
They're getting sweaty and they don't want to stay next to each
The
other.
volume is getting, whoa, what happened? The volume got smaller. So with water, it's kind of strange, as it goes into a liquid state, that it kind of condenses and contracts and gets a little bit smaller in its volume. That's why water has a greater density than ice. That's why ice, does it sink or float? Floats. That's why the icebergs are on top and not on the bottom. Otherwise, the world as we know it would be a lot different, right?
This explains why steam is such a big gap, because oxygen particles seem to stay really close together.
All right, I'm going to heat it up. As I heat it up, we're going to a gas.
Like flies.
Okay? I'm heating it up. Okay, so this is very hot. I now have this gas, right? What do you still see?
They're still connected together.
They're still connected together.
So you have to do
What'd you say? The particles are still together. The atoms are still together. What do you still see? H2O. Do you understand that? Who can we cancel out now? Who is not correct in one of our options? Lucy.
What?
Well, Lucy says that it's separated hydrogen and oxygen.
But they're still connected.
You can't have hydrogen.
They never do disconnect. They're just
Exactly.
They stay together.
The molecules separate.
Ah.
Okay, so the molecules separate. Not the hydrogen and oxygen, because it's always going to be H2O. That's the compound. And those molecules of H2O are what's going to be separated from each other, but the hydrogen and the oxygen are always connected. See this? It's always red and white, red and white, red and white. So we can we see from here that Lucy, who said the bubbles contain oxygen and hydrogen, that's separated from the water. No, that's not what we see. When we see that was whenever we did the hydrogen peroxide and used the manganese dioxide as a catalyst to release the oxygen from the H2O2. Do you remember that one? Okay. So we had the H2O2, and then this is the only way that oxygen could be freed was by this catalyst. So the only way that we could get that was then we had water, and then we had a gas that was released. It took a chemical reaction. Do you remember what happened after that chemical reaction? What about the temperature of the container? Very hot, right? So it took a lot of energy for this to have a chemical reaction. It released a lot of energy for that chemical reaction. Whenever you're heating something up, it's just changing states, okay? And it's not necessarily a release of energy in such a thing like this. All right? So it takes a lot of energy to be able to release that one oxygen. So Lucy's not correct here. But let's look at some of the other options. What about Dad? He said it's heat. Does heat take up space?
No, it's energy.
It's energy, so it doesn't have volume, it doesn't have mass, so that can't be right. What about Calvin? Bubbles filled with air.
Because air is lighter than water, so it'd have to float up to escape.
Okay, great. Air is lighter than water. What about H2O as a gas?
Steam.
Steam actually has little particles of water in it, but you're right. Water, we call it water vapor instead. But like water vapor is H2O. Is the gas form of H2O lighter or less dense than the liquid form of H2O?
Yes.
Yes. So it would rise to the top two, but you're on the right track there. Okay?
So it would probably be right.
That's that. Oh, well, let's wait. Yes.
No matter what, it's just
Good point. Okay, so what Daly just said was that in order for us to have what is, by the way, what is in air? What is in the atmosphere? Which compounds and molecules? Let's start with the most abundant. Raise your hand if you know what's the most abundant gas in the atmosphere, Atticus. Nitrogen. So we have N2. And does anybody know what the percentage is of nitrogen? Jacob?
Around 80%.
Around 80%, we say 78%, right? Exactly. Okay, what's the next best or next most abundant, Deontay?
Oxygen.
Oxygen. Very good. And anybody know some of the trace gases, or how much does oxygen make up?
21%.
21%. Thank you, Pearson. So 21%. So now we have these trace gases, and let's just name some. Just yell them out.
Argon, neon.
Argon.
Carbon dioxide.
Carbon dioxide.
Hydrogen.
Hydrogen.
Helium.
Basically, all of those noble gases. What are some compounds?
Yeah, right.
What compounds are in the air? CO2, carbon dioxide. H2O. Good. Now, I want you to understand. If we go back in our mind and think conservation of mass, when we did the chemical reactions and things, what you have in the reactant side must be in the product side. We cannot create or destroy matter. Okay? Let's think about what's in that bubble. If it's air, what does that mean that's going to be in there? Nitrogen, oxygen, argon, neon, things like this. Nitrogen is the most prevalent, so let's start there. Where is it going to get the nitrogen from? Can it get the nitrogen from the water? No. You see what I mean? It can't get it from there. It possibly could get it from the air that's inside the tea kettle, but where's that air? On top. As soon as you put a liquid in, it's more dense, it sinks to the bottom, right? So it can't get the nitrogen. So the bubbles right here, these bubbles, there can't be nitrogen in there because they're originating from the bottom. So what is it? What is it that is in this bubble?
It's in water.
So let's go to grandma. Invisible form of water. Yeah, H2O, H2O. It's basically water vapor. It's a gas form of water. So what we're trying to show you is that water in the beginning, water in the end. Grandma's correct. And she's always correct. You know that. Come on. She's got wisdom.
She's like magically invisible.
Well, no, not magically invisible, but basically it's invisible in that you cannot see what's inside of it. Yeah. Well, let me tell you this about these little assessments, these little formative like probes. These are meant to be, I won't say, tricky is a good way, I guess, to say it, but basically it's meant to be ambiguous, meaning that it has more than one possible answer, but it has a best answer, and it's really trying to make you dig deep into, and to get some of these wrong, really, to make you think. I could give the same thing to other teachers, to your parents, and I guarantee you, most of the time, they're not going to get the right answer. Because you have to understand a whole lot in order to get the right answer here. Even when I look at them, I have to really think. And then, I have to go look at the resource to make sure. You know? So, it's supposed to make you think. So, if you get any of these wrong, no te preocupe. Don't worry about it. You know, it's meant to make you think. That was Spanish, Mark. I'm sorry. I know you looked confused.
You got it right.
I was the one who looked confused.
Who got it right in the beginning?
Yeah, you seriously got it right. I'm telling you that he's serious.
Who got it right in the end?
I got it right in the end.
Say basically did.
Well, after I see a good explanation, and don't, hey, by the way, don't scratch it out. Don't, please don't erase. Don't erase. Why, you know, hey, me as a teacher, I want to see that you guys started with one answer and then ended up with another. It is a good thing. It is a good thing for me to see that you didn't have it right in the beginning and you actually have learned something in my classroom. That's like a reward for me. That's better than this chocolate.
We make, the happier you are.
Huh?
Aren't those from the bubble gum and chocolate?
Yes, this is from the bubble gum and chocolate.
These are old
Expired.
Does anybody want some bubble gum?
Me.
Speaking of that lab, why was it that the bubble gum and chocolate did not mix well?
Because they have the same
Hold on,
layer.
I want one person. Serena? One had water and one had what? One had water, one had oil, okay?
That's really good.
Polar, non-polar. Wait, though. They dissolve.
Well, we had the saliva in our mouth that helped it because it has water in it too.
Okay. Was it the polar part though? Because listen, if you're chewing up a piece of gum, it doesn't become soluble, right? That's a good thing. The sugar, you get the sugars out, but the gum itself doesn't dissolve in your mouth. Otherwise, that would not be very good. What's in the chocolates? Oils. Is it polar or non-polar? Oils, are they polar or non-polar? Non-polar. So the chewing gum itself was non-polar too. Therefore, it started to break each other down and it became soluble in your mouth. Was it fun then? Okay. So Grandma's correct. Take a moment, if you haven't already, make a quick statement of truth based off of what you now know. And let me go ahead and Deontay, if you will, take these up.
Thank you. You can see the bubbles.
I'm not tasting that. Horrible.
Why are you wearing
Again.
Okay, while you're waiting, I want to go ahead and share with you. I want to go ahead and share with you something that's in the news today. It's on the front page. Does she look familiar? Okay. She was in Washington, D.C. yesterday, basically talking before all of the Congress senators, talking about the need for schools like ours all over the country. Okay, so it's pretty cool. Really, really cool. She was able to talk to. Thank you. Put it in the box, please. But she was there basically saying, give failing schools all over the nation a choice between charter schools or magnet schools like ours. And I think that's really cool that our principal was speaking before the nation, and it was on that TV channel that nobody watches called C-SPAN.
I watched that with the inauguration.
Oh, well, that's a good time to watch it.
My girl watches it all the time.
Yes. I hope you go to sleep at night. All right, here we go. So yesterday, some of you were here for our exploratory. Raise your hand if you were here to make the glaze. Fantastic. We're going to have 2 parts today's class. Okay, 2 parts. Okay? The ones that were here yesterday working on the glazes, you're going to take the next step. Those of you that were not here yesterday, you are going to be making the glazes if you can be responsible enough and handle yourself appropriately in the lab. Because I can't be in both places at the same time, I'm going to be in the middle, back and forth. I'm really trusting you guys to be able to handle yourselves as young adults. You have proven yourself before, and you're going to prove yourself again today to be able to handle that. Okay? The way the lab looks now is the way that it's going to look at the end, if not better. Okay? Nothing's in the sinks when you're finished. They should all be cleaned up, soaked in water, using dish detergent, and hung up to dry. Okay? We're going to use safety precautions, glasses on at all times, for those that are back there at the lab tables. For those that are up here at your tables here, you're going to use newspaper underneath your clay creations. Okay, now, let me back up. This is what we're doing. Half of you are going to be using the recipe that you now have and are pasting into your notebook like this. You're going to choose a color. It's either going to be blue, brown, orange, or emerald. I'll tell you right now, I need more orange. Okay? If that's an option, that's the one I really need more of. You're going to write in the amounts. It says 65%. This is a ratio. Okay? 65%, 15%, 20% equals 100%. You're going to multiply that by the desired amount. The desired amount must fit into a Ziploc bag. Yes.
Is it emerald like green?
Yes. And we have lots of emerald. So if anything, either one. And Red just said something. It doesn't look too good. Let me just ask you. Our big question yesterday, and it's our question for today, and what I want you to as you make these observations and do the lab back there, I want you to ask this question right here. Is making clay glazes a chemical reaction? You don't have to answer that right now, but I do want you to be able to kind of walk through that in your observations. You're looking for the indicators of change. Looking at our anchor chart, you're looking for the indicators of change. What was the indication that there was a chemical change? Okay? So, back to this. 100 grams seems to work well, and it also makes a nice math problem for you that's not too hard to solve. 100 times 65%, 65. Okay. But don't make a mistake down here, because these are your colors. After where it says water added, these are the colorants on each one. Okay? That's only 4 grams. That's only 1 gram if you're doing 100 as your 100 grams mass of total. Okay? Each of these chemicals are on the cart back there and on that lab table. So what you need to do is you have to find the appropriate bag with, and it's written on there, all except for silica oxide. Silica oxide is in a big brown bag, and it's got Si2O3 on the side. You're going to use a spoon in order to get the appropriate amount. I would use a little plastic cup if you can find one. Use that one plastic cup for all of your measurements. Just wipe it out with a dry paper towel. Don't use water, because then it becomes a mess. It sticks to the side and everything. So we're just going to use that. We have our precision balances that we have been blessed to have. We just got them this year, so we want to take care of those. We only have 2 of those, so you have to share. Use the triple beam balance, and then make sure you have the right amount. Okay? If you do, then you can use the triple beam balance every time. I love seeing you guys use that anyway, because it shows a lot more understanding. Okay? So, all that gets put into one